right. Now for mutar rotation is the interconvertibility or the interconversion of the alpha anoma with the beta anoma in solutions. So the interconvertibility of the alpha anoma with the beta anoma in solutions is what we call mutar rotation. Now for alpha glucose, the alpha anoma have a specific rotation of plus 112.2 degrees, while the beta anoma have a specific rotation of plus 18.7 degrees. But at the end of the day, in solution, we observe that the glucose molecule achieve an equilibrium rotation, which is around plus 52.7 degrees. Now, what is the reason for this? So in solution, glucose have a specific rotation of plus 52.7 degree, but the alpha anoma is 112.2, the beta anoma is 18.7. Now, this specific rotation in solution is an equilibrium between the alpha and the beta anoma. So it means that when you put glucose in solution, somehow, the alpha anomas present or we interconvert to the beta anoma such that there will not be an equilibrium. That equilibrium leads to a new rotation, which is around plus 52.7 degrees. Now, I'll look at the mutar rotation for fructose molecule. Now, remember this is glucose, the glucose molecule, the pyranose form. Remember this is alpha anoma because the OH is down. We said that earlier. So for fructose molecule, please look at it. Well, look at it. This is what we call mutar rotation, the interconvertibility of the alpha and beta anoma, or the existence of the alpha and beta anoma in equilibrium. It's known as mutar rotation. Mutar rotation. It happens for all sugar molecules in solution, especially exotic sugars. So for fructose, I'll quickly look at fructose. Now for fructose, very fast. Fructose is CH2OH, just like glucose, but is a functional group isomer to glucose. And we have OH to the left, H, COH to the right, H. So 1, 2, 3, 4, 5, 6, then CH2OH. Now, this is fructose, everyone. Now, if I should show you remember fructose is a keto sugar, so fructose won't form hemiacetal form, it want to form hemiketal form, which leads us to the outward projection, the cyclic form of fructose. So what happened? This is the penultimate carbon. So this attacks that guy, the alcohol group attacks the ketone group and will form a ketal, an hemiketal. So at the end of the day, I explained earlier, the O here takes the H here, so it becomes OH. Then this C takes the O. Yeah, the C takes the O. So such that I can now adjust the O to the middle, just for two-dimensional sake. So at the end of the day, fructose, which is a keto exos, we form a 5-member ring structure. Why is it 5-member ring? So this is 1, 2, 3, 4, 5. 5-member ring. And that 5-member ring structure for fructose is like furan, just like furan. Something like this. It's like furan. Yes, something like furan. This is furan. So 5-member ring structure of a sugar is known as the furanose form because it resembles the furan. It's known as the furanose form. So the furanose form of fructose, will look like something in this manner. So the furanose form of fructose looks like something in this manner. So we're going to have something like this. So we have, this is the anomeric carbon. And the anomeric carbon has a CH2OH. Okay, that is CH2OH, and usually carbon 2. So this is 1, 2, 3, 4, 5, and 6. So it has So that is C. So this is carbon 2. Carbon 2 has OH, just has OH, and there will be a H there. Yeah. Okay, let's see. Tetravalency. Okay, there's no H. 1, 2, 3, 4. So it has carbon 2 has 4 bonds. So it just has an OH. So this carbon 1, pardon me, this carbon 2, that's an OH. Now carbon 3 is going to have OH up. So OH left is up, take left to be up, right to be down. See? Right. OH is to the right for carbon 4. OH H up. Now this carbon 5. Carbon 5 has H and it has CH2. Just pardon me. I'm going to make an exception for carbon 5. Let me just invert it. I'm going to say this is so I'm going to say carbon 5 has a CH2 OH there, then an extra H. CH2OH there, then an extra H. Yes, that's for carbon 5. So this anomal for glucose, this anomal for glucose, this anomal for fructose, pardon me, is known as the alpha fructose or the alpha fructofuranose as they will call it. Well, let's just keep it simple. Alpha fructose. Alpha fructose is a furanose form. Why is it a furanose form? Because fructose, the keto exoses and even the aldopentoses, they form furanose form in their cyclic structure. We're going to look at that in our biochemistry videos. So they form 5-member cyclic structure, 5 members. So 5 member is furanose, 6 member is pyranose. So fructose form the pyranose form. So this is the alpha pyranose. This why is it alpha? Because this alpha carbon, also pardon me, the anomeric carbon, on the anomeric carbon, the OH is downward. The OH is downward, so it's alpha form. So what Mutarotation is simply saying is that the alpha form and the beta form can exist in equilibrium. So when the alpha form can easily interconvert to the beta form and an equilibrium will exist, such rotation is known as Mutarotation. So such rotation, we see in glucose, as I explained, you see the change in rotation, the change in optical rotation. So such change in optical rotation, when you place a carbohydrate molecule in solution, is known as known as Mutarotation. Yes. So having known Mutarotation, let's look at the reactions of monosaccharides. Reactions of monosaccharides. All right, for the reactions of carbohydrates or reaction of monosaccharides, I'm going to use monosaccharides as case study. We're looking at the first one, which is oxidation. Now, glucose, which is the most common monosaccharide found in grape sugar, and also fructose found in fruit, it's called fruit sugar. Now, on oxidation with mild reducing agent, so if you oxidize glucose with mild reducing agent, you get gluconic acid. Yes, with mild reducing agent, you get gluconic acid. Even when you oxidize fructose with mild reducing agent, you get gluconic acid. Why? Fructose, pardon me, can easily, fructose is a ketone sugar. Please take note, all monosaccharides are reducing sugar because the ketone group can easily rearrange to an aldehyde group via indiol rearrangement or what we call Lobry-Dibiner rearrangement reactions. So even when you oxidize fructose, though it's a ketone group which cannot be oxidized, when you oxidize fructose, you also get gluconic acid. Yes, because of the rearrangement. So glucose can, my point, fructose can easily rearrange to glucose. Fructose can easily rearrange to glucose. So when you oxidize glucose with mild reducing agent, or you oxidize aldoses with mild reducing agent, you get adonic acid. So adonic acid is more like a general name for aldose that can be oxidized. So adonic acid. So how is adonic acid formed? How is adonic acid formed? For adonic acid, if this is glucose, I'll take carbon 1. So for instance, this is carbon 1. There's a long chain between, and this is our carbon 6. So carbon 1, there's 2, 3, 4, 5. 2, 3, 4, 5 inside here, which will, if you are looking for the structure of glucose, just take the video backward, you get it. So they have 2, 3, 4, 5 inside here. So this is 6. So on gluconic acid formation, only carbon 1 is oxidized. So this aldehyde group, it oxidizes to acid group CH2OH. So if this is glucose, carbon 1 and 6, this is 1 and 6 also, this should be gluconic acid. Yes, gluconic acid. So that's how you oxidize them. Even if it was galactose, we form galactonic acid. Yes. So all aldoses or all reducing sugars or monosaccharide can be oxidized. For mild reducing agent, which type of reducing agent, or pardon me, for mild oxidizing agent, which type of mild oxidizing agent can be this oxidizing agent? This oxidizing agent can be KMNO4. Please take note. It can be K2CrO2O7, alkaline conditions. Yes. It can be Tolling's reagent. Tolling's reagent is ammoniacal silver nitrate. This is how we express it in exam condition. Tolling's reagent, ammoniacal silver nitrate. So if I take everything on the board out, I want to show you Tolling's reagent with formula. So let's say I want to show you Tolling's reagent with formula. So Tolling's reagent can be, please watch this, Tolling's reagent can be AgNO3 in NH3 solution, or we can put it as NH4NO3 Ag. So anyhow you put it, let me express it all. So let me say NH4 plus AgNO3. So ammoniacal silver nitrate is Tolling's reagent. Now also, this reagent, outside being Tolling's K2CrO2O7, can be Fehling's solution. Fehling's solution is copper 2 complex or copper 2 tartarate complex. So copper 2 sulfate solution in tartarate. Yes, copper 2 tartarate complex. It can also be Benedict solution. Benedict can also be Benedict solution. Benedict is copper 2 citrate complex. So both Fehling's, Benedict, K2CrO2O7, KMNO4, Tolling's reagent can all oxidize glucose to gluconic acid. In the formation of adonic acid, carbon 1 is the only one that is oxidized. Carbon 1. That's why it is termed mild oxidation. It's called termed mild oxidation. For vigorous oxidation, so we can call this one 1A. Take it. For vigorous oxidation, not using any of these oxidizing agents. Before I even comment on vigorous oxidation, it should be noted that Tolling's, Benedict, and Fehling's are used to test for reducing sugar, such as glucose and monosaccharides. Yes, Fehling's, Benedict, and Tolling's are used to test for reducing sugar, such as glucose and monosaccharides. For positive test on Tolling's, there's information of a silver mirror. Silver is produced. For Fehling's solution, there is the production of a red precipitate of copper 1. For Benedict solution, there is information of red precipitate of copper 1 also. So please take note. Fehling's, Benedict, and Tolling's can be used to test for glucose, reducing sugars, or the hard doses. Okay. Now, for the second type of oxidation I will quickly talk about is very strong oxidizing agents, or using powerful oxidizing agents such as HNO3 and fuming sulfuric acid. So if I should use HNO3 on glucose like this, HNO3 on glucose, I'm going to form glucaric acid. Yes, glucaric acid. Yeah, we're going to form glucaric acid. Now, for glucaric acid formation, you observe that the oxidation, this is 1. Let's say there's 2, 3, 4. Let me make it long. So there's carbon 2, 3, 4, 5, and this is my carbon 6. Yes, 2, 3, 4. This is my carbon 6. So like that. So 6 is my carbon 6. So if I oxidize with concentrated HNO3, I am going to observe that both carbon 1 and carbon 6 will be oxidized. So I will have COOH at carbon 1 and COOH at carbon 6 because the alcohol groups can be oxidized to alkanol and later to alkanoic. So you see for glucaric acid, when glucose is oxidized to glucaric acid, you form a dicarboxylic acid at carbon 1 and carbon 6. Carbon 1 and carbon 6. So aldoses undergo this reaction. So if it's an aldose, you form aldaric acid. So the general acid formed when aldoses are placed in HNO3 is known as aldaric acid. It's a group of acids called aldaric acids. So if it is galactose, you get galactaric acid. Yes, galactaric acid. Galactaric acid. So this is for powerful oxidation. This is powerful oxidation. But there's a special oxidation I would like to add as a bonus in this course. A special oxidation I would like to add as a bonus. Now, how is that special oxidation? Now, that oxidation in some special enzymes, I'll just comment on it, not throw light too much light. In some special enzymes, reagents do not do this reaction. Special enzyme, glucose can be oxidized at only position 6. So only position 6 will be oxidized. And when glucose is oxidized at only position 6, you form glucuronic acid. So in general, we use the word the uronic acid. Uronic acid. So uronic acid is formed when only position. So let's say this is glucose, this is 1, and CH2O, this is position 6. So uronic acid formation involves position 6 will be an acid to be oxidized to an acid group. So when only position 6 is oxidized in an aldose sugar, such acid is known as an uronic acid. If it was galactose, we form galacturonic acid. So I say when galactose, so I mean directly say that when galactose is oxidized at position 6 only, you form galacturonic acid. I say this formation is done in the presence of enzyme. Chemical reagents might not be able to carry out these reactions. Yes, might not be able to carry out this reaction. So for glucose, enzymatic oxidation to galacturonic acid. Where is oxidation in the formation of uronic acid? Which of the carbon is oxidized? It's carbon 6. So that moves us to reduction. All right. For reduction, in the presence of reducing agents such as LiAlH4, glucose, which has been our case study, can be reduced to sorbitol, or what we call glucitol. So if you reduce glucose, this aldehyde group is going to be reduced, because if you reduce aldehyde, you get alkanones, primary alkanones. So the aldehyde group will reduce to a primary alkanol and CH2OH, yeah, up and down. So we get what we call a glucitol. So this is a glucitol. Or we call it a sorbitol. Glucitol or sorbitol. All right, now that's glucitol. So glucitol or sorbitol. Now, generally, aldoses, when you reduce them, you form additol. So if you have an aldose sugar, on reduction, you form additols. So they are generally called additols. So for galactose, you form galacitol. For fructose, remember fructose can easily tautomerize to glucose. So for fructose, when you reduce it, you form sorbitol also. So sorbitol or glucitol is a sugar alcohol which can be used as artificial sweeteners. Yes, they are also sweet like glucose. I use them as sweeteners. So that's for reduction of aldehyde. So the next reaction we'll quickly move on to is addition reactions. Yes, remember, aldehydes and ketones have nucleophilic centers, or centers that are electron rich, than we can add to. So and these aldehydes and ketones are found on sugar. So addition reaction. So for instance, we have an aldehyde like this. I'm going to elongate this aldehyde or open it up. So this is an aldehyde. So let me put double bond OH. So let's use glucose. This is carbon 1. Let's take it down to carbon 6. Yes, 1 to 6. So if you had a substance like HCN, or the way they put it in some reactions, you're going to see KCN in HNO3 or in HCl. When you see something like this, you know that this two is going to produce HCl. The H is going to take CN and the K is going to take Cl to form potassium chloride salt as the minor product. Then form HCN. Now, this HCN can react with this aldehyde group. Now, this aldehyde group is electron rich. So what normally occurs is that the H takes the OH and the CN will take the carbon. So normally we say this is like a partial negative on the O, positive on the guy. So this guy will form positive and negative. So the positive takes the negative, negative takes the positive, like that. So at the end of the day, if this is glucose, I just showed you just carbon 1 and 6. If that is glucose at the end of the day, we are going to have something like C. Now what's going to happen is that, so let me take my H here. CN will be added to this guy and will form OH here, because the H takes the O. So the double bond is going to break. So one of the bonds has broken. So this is we take down to carbon 6, CH2OH. This is our carbon 6 now. So if you observe what has happened, glucose has been elongated. What I mean? Before, glucose was 6 carbon, 1 to 6. Now glucose now have 6. So this is an extra carbon. So this is now an extra carbon glucose. This cyano group is now added. So this compound form when glucose reacts with HCN is known as glucose cyanohydrin. Glucose cyanohydrin. Glucose cyanohydrin. So glucose plus HCN or plus KCN in HCl will produce on your arrow like this. You can see on your arrow, at times you can see on your arrow like that, you can see we have KCN in HCl. Yeah, it's going to produce HCN to form glucose cyanohydrin. Glucose cyanohydrin. So that's for addition reaction. That's for addition reaction. So cyano group, the cyano group is known as a chain elongator. That means I can use the cyano group to elongate this chain. So I can use cyano group to change a 4 carbon monosaccharide to a 5 carbon monosaccharide from tetrose to pentose or from pentose to hexose. So they are chain elongators. That's for addition. So the fourth one I'll quickly look at is fermentation. Yeah, fermentation, very important in industries. So for fermentation, so glucose, which is the most common, can be fermented. Yes, fermentation. Glucose can be fermented in the presence of yeast to alcohols. So if I have glucose C6H12O6, this is the general formula for glucose, or general formula for hexose monosaccharide. So glucose can be fermented. Glucose can be fermented in the presence of yeast enzyme to alcohol. In the presence of yeast enzyme, such as zymates. Yeah, these enzymes are zymates to alcohol. So I'm going to get 2 molecules of alcohol, 2C2H5, C2C2H5OH plus 2CO2. So CO2 is going to come out as a byproduct plus 2CO2. CO2 is going to come out as a byproduct or as a bygas. So this is fermentation. This is fermentation of glucose. Fermentation of glucose. So this is fermentation. Now the fifth reaction, I'm going to quickly make you undergo. The reactions are very simple. They're very simple if you are used to your common chemistry. They are simple. They are not technical reactions. So, but there's this last one I'm going to do is kind of technical. It's kind of technical, and it is the condensation of glucose. So condensation reaction. So usually, if you look at our chemistry of alkanals and aldehydes, chemistry of alkanals and chemistry of alkanals and alkanones, or chemistry of alkanones and ketones, or aldehydes and ketones. So if you look at this chemistry very well, these two group aldehydes and ketones, they usually undergo condensation reaction with ammonia derivative or amines or amine derivative or amino derivatives. Yes, let me take you back a little bit. So assuming I have ethanol, this is ethanol. If I react ethanol with hydroxylamine is OHNH2. This is hydroxylamine. If you react ethanol with hydroxylamine, let me write it in a proper way, which I get my mechanism. So let's say H2NOH, hydroxylamine. So what occurs is that the O, so this is ethanol, pardon me, so double bond O, I have H. So what normally occurs is that the H2 takes the O, such that there is the elimination of water. So what becomes our product? Our major product becomes CH3, C double bond N, CH3C double bond N, yes, CH3C double bond N, OH. So CH3 double bond N, OH. That's become our product. So I'll write it here for clarity. So let me take it up a little bit. So our product can be, our major product can be, let's just say CH3, C double bond N, OH. Yes, this compound that is formed is called an oxime. So when alkanals react with hydroxylamine, we form aldooxime. When alkanones or ketones react with hydroxylamine, we form ketooxime. So usually there's the elimination of a smaller molecule such as water. That's why it is called condensation. So in the same manner, glucose can undergo condensation. So with ammonia derivative, yes, condensation with ammonia derivative such as hydroxylamine, and let's say this is glucose. Normally I show carbon 1 and 6 for a safe space for explanation. Now, so I'm going to have now this hydroxylamine. So this hydroxylamine is H2NOH. So normally the H2 and the O is going to leave as H2O. So what I'm going to have is going to be this carbon 1, this carbon 6. Get me? So I'm going to have C, there's a H here, double bond N, OH. So this is carbon 1, this is carbon 6. So CH2OH. What is the name of this compound formed? It is called glucoseoxime. So glucose plus hydroxylamine, I get glucoseoxime. Yes. What about if it was fructose? Fructose plus hydroxylamine, I get fructooxime. Yes, fructooxime. That's an example of a condensation reaction. Don't forget, with the formation of a smaller product such as water. That's why it is called condensation. So this with hydroxylamine, I'll do reaction with phenylhydrazine, and I think I'll start with hydrazine. I'll do phenylhydrazine. So we'll see how it works. I'll start with hydrazine, then I'll do phenylhydrazine. So we'll see how it works. So with hydrazine, hydrazine is a diamine. So hydrazine is NH2NH2. In case those of us that don't know hydrazine, NH2NH2. So with hydrazine, if glucose reacts to hydrazine, that's the H2 olivine. Yes, that's the H2 olivine. So the byproduct is also water. That's the H2 olivine. So with hydrazine, I'm going to have N to another N, NH2. So this compound formed when glucose reacts with hydrazine is known as glucose hydrazone. Please don't forget that. glucose hydrazone. So glucose plus hydrazine, and we get glucose hydrazone. Yes, glucose hydrazone, a yellow precipitate of glucose hydrazone. Yes. So we've done with hydroxylamine, glucose plus hydroxylamine, glucose or zyme, glucose plus hydrazine, glucose hydrazone. I'm showing you the mechanism. Which group is affected by this condensation reaction? It is the alkanal or the alkanone group. For the alkanon here is affected by this condensation. Yes, the O leaves here and the H2 leaves from the ammonia derivative. Then you join the two groups after its addition. So this is glucose and the formation of glucose hydrazone. Now, this special one I want to look at last is the reaction with phenylhydrazine, which seems sort of special. Yeah, reaction with phenylhydrazine. Now, for phenylhydrazine, something special occurs. When glucose reacts with phenylhydrazine, that's why it is used as a quantitative test, quantitative and qualitative test of glucose or reducing sugar. Not just carbon 1 is affected. Carbon 1 and carbon 2 is affected. So I'm going to put carbon 2. So I'm going to put carbon 2 as COH H. So let's say it's H. So let's say H, then OH. So when glucose reacts with phenylhydrazine, carbon 1 and 2 is. So I've just, for this glucose molecule, I'm showing just 1, 2, and 6. So please don't forget that. For glucose molecule on the board, we are showing just carbon 1, 2, and 6. Carbon 1, 2, and 6. So phenylhydrazine is represented like this. So let me show you phenylhydrazine. Phenylhydrazine is a phenyl group C6H5 NH2. So one of the H in the hydrazine is replaced by a phenyl group. So when glucose reacts with phenylhydrazine, from the names we have been seeing since, we will form what we call glucose phenylhydrazone, which is known as osazone. Yes, that's osazone formation. Osazone formation. But the mechanism is kind of different. The mechanism is kind of different. As the reaction for phenylhydrazine, being that phenylhydrazine is stronger than hydrazine itself, the attack occurs at two positions. So at two positions. So it is two molecules that usually react. So two molecules of phenylhydrazine attack position 1 and 2 of the glucose, such that, let me just keep to my product to save time. I'm going to have CH now, double bond NH, double bond N to NH, which has the phenyl group C6H5, going down to carbon 2. Carbon 2 was affected. So the H2O leaves from carbon 2. Then we have double bond N, single bond NH to C6H5. So then we have our last, then we have the other 2, 3, 4, 5. Let me just show carbon 6. And this is carbon 6. So this is carbon 1, carbon 2, and carbon 6. So when it reacts with phenylhydrazone, being that phenylhydrazone is very strong, attack occurs at two positions, 1 and 2. So this is glucose reacting with phenylhydrazone. I form glucose reacting with phenylhydrazine, pardon me. I form glucose phenylhydrazone. Glucose phenylhydrazone, which is popularly called osazone, a yellow precipitate. I said this can be used for the quantitative test for glucose. Yes, a quantitative test for glucose. So this is one of the important condensation reaction with phenylhydrazone. So I'll leave it on the board so you can look at it. You can look at it very quickly. So you get it. So you see how it is done, and you take it down. You can see very quickly. very, very quickly. So you observe it. See how it is done. And mind you, water molecule is formed. Now it will be two water molecule because condensation occurs at two positions. The water molecule is formed, 2H2 is formed. That's osazone formation. Osazone formation. So it's going off. So for the last reaction is a very simple reaction, which is dehydration. So when you dehydrate monosaccharides in general, glucose and co, when you dehydrate monosaccharide in general, monosaccharides are like carbon having water or hydrate of carbon we explained in the beginning of this video. Hydrate of carbon. So when you dehydrate carbohydrates in general, be it starch, with good dehydrating agents such as concentrated H2SO4, the sugar is going to be dehydrated. The sugar is going to be dehydrated, and we have a black mass of carbon. So at the end of the day, we have 6C plus 6H2O. So this we have a black mass of carbon. Black mass of carbon. This black mass of carbon is popularly referred to as sugar charcoal. So when you dehydrate sugar, when you place sugar in H2SO4, you get a black mass of carbon, which is known as sugar charcoal. This can also be seen when you put table sugar. Table sugar, which is sucrose, when you put it in concentrated H2SO4, the sugar turns to a black mass. A black mass. So that's known as sugar charcoal. Sugar charcoal. So, but basically, monosaccharide can be dehydrated. I think this is the sixth reaction. Monosaccharide can be dehydrated to a black residue or black mass of carbon, which is referred to as sugar charcoal. So until the next video, or carbohydrate number 2, until carbohydrate number 2 is going to be a bye for now. So this video has been very, very helpful. It has a lot of details when it comes to monosaccharide, including the reactions. So we have to end it here and take the next video to the second carbohydrate. So carbohydrate 2. So if this video is helpful to you, after watching it is helpful, don't forget to always click the subscribe button and like the video so your friends who also need the videos from other universities can see them. Until the next video, I will see you when I see you next. Thank you very much for watching.